Welcome to Leetcode JavaScript, a channel where we solve every single Leetcode question using JavaScript. Today we have 222 count complete tree nodes. This is a medium question. Given the root of a complete binary tree, return the number of nodes in that tree. According to Wikipedia, every level, except possibly the last, is completely filled in a complete binary tree, and all nodes in the last level are as far left as possible, and it can be between 1 and 2 to the h nodes inclusive at the last level. You gotta design an algorithm that runs in less than O(n) time complexity. Now, this problem might seem extremely simple initially if it were not for this caveat that you need to do it in less than O(n) time, because if you were just able to traverse through the tree once, you would just get the length of it and it would be almost trivially easy to do so. But since we do need to do it in less than linear time, there's a somewhat clever trick that we're gonna do. And as a general rule of thumb, whenever we need to do something in less than linear time, there's a good chance we're gonna have to be using binary search or something similar to binary search. So I have a simplified way to do so. I'm gonna show it to you guys. So we're gonna be having a left function. And this left function is gonna return me the length of everything that's to the left of my current node, essentially. And the way to do it is that if node, meaning if it is null, we're gonna return 0, and otherwise we're gonna return left node that left and +1. And this simple recursion essentially gives us how many nodes we have to the left of the current node that we're taking a look at. And we're gonna do the same for this. I'm gonna call it right, and it's gonna be the exact same, essentially just changing left to right. And this is gonna give us how many nodes we have to the right of a given node. Now, to do this simplified binary search here, you could do a regular binary search with middles and lefts and rights, but I think there's a clever way to do so. We're gonna need a transverse function. I'm gonna call it trans, and we're gonna have a node as our input, and we need a couple things. We need the left length, add left, or rather ln, let's call it like that. It's gonna be left of node, and we're gonna have rlen, and it's gonna be right of node. Essentially, you're just counting how many nodes you have to the right of view and to the left of view. Now, the following step is a bit mathematical, but it makes a lot of sense if you're familiar with binary trees, or even you read the description closely. We want to check whether the left length and the right length are the same. And if that's the case, it just so happens that we know that the tree is complete in the sense that there's no more additional space for more nodes. For example, if this were to be the case in tree number 1, there would be a 7 over here. So we want to check whether that's the case, because that gives us an easy way to return things. And it ln is equal to rlen. In that case, we're gonna return math.pow between 2 and ln -1. And essentially we're just following what we've been told here, that there's between 1 and 2 to h nodes at the last level, where h is the height. And we're also going to be using a simple recursion case here, in case this is not the case. And otherwise we're going to return trans of node that left plus trans of node dot right, and all of that plus 1. Okay, so far so good. And finally, we're gonna return trans of root. And remember, root is the initial input that we're given. Now let's run this code, and then I'll explain something else about this code. And if you really think about it, what you're actually doing here is trying to figure out how many nodes are at the last level. Because you know for sure every single level that's not the last one is going to have the maximum amount of nodes possible. So you don't really have to do any computations or any transversal rather to figure out how many there are. The main thing you're concerned with is how many there are all the way at the last level. And the easiest case is when the thing is full, and you can return this q to the l of to the h minus 1. And otherwise you are just using simple recursion, and in this case it works out in a very similar way to a simplified binary search, in which every single time you go to the next step you're throwing away half of the nodes. The other half of the nodes is no longer relevant to you. For example, when we go to 1 to 2, everything that's right to up to you're just throwing away, and that's approximately half of the nodes for the average case. Now, what is the time complexity of this? The time complexity of this is actually O of log of n squared. And why is that? We're doing log of n to the left and log of n to the right. Essentially, we're multiplying those two actions. And another way to show this, or to write this, would be log of n times log of n. And these two things are the exact same thing, but maybe writing this way makes a bit more sense what the time complexity might be. Space complexity is actually kind of high. It depends on the implementation of the stack trace, but in general it's going to be something like 2 to the n, because we have so much recursion. In the worst case scenario, we'll take a look at everything half of the time. It's probably going to work out something like 2 to the n. And that's it for today. Thank you so much for watching. Don't forget to like and subscribe.